Alright, so today we're talking about something that sits at the very heart of every data pipeline you've ever built: DAG dependencies, fan out, fan in, and sensors. Now, I know DAG sounds kind of intimidating, like some heavy computer science term, but honestly, it's one of the most intuitive concepts in data engineering once it clicks, because all we're really talking about is the order in which things need to happen: what runs first, what runs next, what can run at the same time, and what needs to wait. That's it. That's the invisible wiring behind every pipeline you've ever seen in Airflow, Dagster, Prefect, whatever tool you're using. And the thing is, getting this wiring right is the difference between a pipeline that hums along beautifully and one that silently produces garbage because something ran before it should have. So let's break it all down. So let's start from the basics. What is a DAG? DAG stands for Directed Acyclic Graph, and I promise that's less scary than it sounds. Let's take it one word at a time. Directed means the connections between tasks go one way. Task A feeds into task B, not the other way around. There's a clear flow direction. Think of it like one-way streets. Traffic only goes one direction. Acyclic means there are no loops. You can't have task A depend on task B, which depends on task C, which depends back on task A. That would be a cycle, and it would mean nothing could ever start running. The system would just be stuck. So no circular dependencies allowed, and graph just means it's a collection of nodes connected by edges. Nodes are your tasks. Edges are the dependencies between them, the arrows that say this thing must finish before that thing can start. Put it all together, and a DAG is basically your pipeline's blueprint. It tells the orchestrator exactly how to execute your workflow, which tasks exist, which ones depend on which, and what the execution order should be. Every time you define a pipeline in Airflow or Dagster or Prefect, you're building a DAG whether you realize it or not. And those dependency arrows between your tasks, those are arguably the most important part because they determine whether your pipeline produces correct results or complete nonsense. Let me give you an analogy that makes this really tangible. Imagine you're hosting a big dinner party, you're making a full multi-course meal, appetizers, main course, dessert, the whole thing. Now, some tasks have a strict order. You have to chop the vegetables before you can stir fry them. You have to mix the batter before you can bake the cake. Those are sequential dependencies. One must finish before the next can start. But here's the thing, while the cake is baking in the oven, you can totally be working on the salad. While the rice is cooking, you can be preparing the sauce. These tasks are independent of each other. They can happen at the same time, in parallel, and that's fan out. One decision, I'm cooking dinner tonight, fans out into multiple independent tasks that all happen simultaneously. But then at the end, you can't serve the meal until everything is ready. The main dish, the sides, the salad, the dessert, they all need to converge to one moment. Plating and serving, that's fan in. Multiple parallel tasks, all need to complete before the final step can happen. And here's the kicker. What if you're waiting for a grocery delivery before you can even start cooking? You keep checking your phone. Has the delivery arrived yet? No. Check again. Still no. Oh wait, it just arrived. Now you can start. That's a sensor, a task that doesn't do any actual work. It just waits for some external condition to be met. Now imagine you try to cook everything one thing at a time, sequentially. Chop vegetables, wait. Cook them, wait. Make the salad, wait. Bake the cake, wait. Your guests would show up and you'd still be making appetizers. You'd eat at midnight. That's what a badly designed pipeline looks like. No parallelism, no fan out, just one slow sequential chain. Okay, so now let's bring this into the world of data engineering. Why should you actually care about getting your DAG dependencies right? Let me paint you a scenario. You're a data engineer at a mid-sized company. You've got a pipeline with about 47 tasks. It ingests data from 5 different sources, runs transformations, builds aggregation tables, updates a machine learning feature store, and refreshes the dashboards that the executive team checks every morning at 9 a.m. One day, a teammate adds a new task to the pipeline. It's a simple aggregation. total revenue by region, they wire it up, it looks right, they deploy it. But they made one small mistake in the dependencies. They set the aggregation to depend on the raw extract task, but they forgot to add a dependency on the currency conversion task that runs in between. So now the revenue aggregation runs before currency conversion happens. It's summing up dollars, euros, yen, and pounds, all as if they're the same number. No errors, no failures. The pipeline completes successfully. Green check marks everywhere. Monday morning, the CEO opens the dashboard. Revenue numbers look weird, way off from what anyone expected. The team scrambles. Is it a data source issue? A business problem? No, it's just that the aggregation ran in the wrong order. Raw revenue before currency normalization. The pipeline didn't fail, it just ran in the wrong order. And that's almost worse than a failure, because a failure, you notice, a wrong dependency, that gives you wrong data that looks right. And wrong data that looks right is the most dangerous thing in data engineering. It erodes trust, it leads to bad decisions, and it's incredibly hard to catch because nothing is screaming at you that something went wrong. Alright, so the first pattern we need to understand is fan out, the one-to-many pattern. Fan out is when a single upstream task triggers multiple downstream tasks that all run in parallel. Picture it like this: your raw data lands in the lake, that's one task. Extract complete. And now, from that single extraction, you kick off 4 or 5 completely independent transformations. Branch 1 calculates user engagement metrics. Branch 2 builds the revenue aggregation. Branch 3 runs fraud detection models. Branch 4 updates the ML feature store. And maybe branch 5 generates the email campaign segments. These 5 branches don't depend on each other at all. The fraud model doesn't need the revenue numbers. The email segments don't need the engagement metrics. They all just need the same raw extract, so they can all run at the same time. And this is where the real power of fan out shows up. Parallelism: if each of those 5 branches takes 10 minutes to run sequentially, that's 50 minutes total. But fanned out, they all start at the same time and finish in about 10 minutes. You just saved 40 minutes of pipeline runtime. And in the world of data engineering, where you're racing against that 9 a.m. dashboard deadline, 40 minutes is huge, but fan out introduces a question you need to answer. What happens when one branch fails? Let's say the fraud detection model hits an error. Should the other 4 branches keep running, or should everything stop? There are 2 schools of thought here. The strict approach says if any branch fails, halt everything. The logic is that downstream tasks might depend on having all branches complete, so partial results could be worse than no results. The lenient approach says let the healthy branches finish. Maybe the revenue numbers and engagement metrics are fine, and the business needs them right now. You can fix the fraud model separately. There's no universal right answer. It depends on your business requirements. But the point is, when you design fan out, you need to make this decision explicitly. Don't let it be an accident. Now let's talk about the opposite pattern, fan in, the many to one pattern. Fan in is when multiple upstream tasks all need to complete before a single downstream task can start. It's a synchronization barrier, a checkpoint where the pipeline says, I'm not moving forward until all of my dependencies are satisfied. Here's a concrete example. Remember those 5 branches from our fan out? Well, after they all finish, you have a final task. Build the executive dashboard snapshot. This task needs data from all 5 branches. It needs the engagement metrics, the revenue numbers, the fraud flags, the feature store status, and the campaign segments. If even one of them hasn't finished, the dashboard would be incomplete, missing a column, showing nulls, or worse, showing stale data from yesterday's run. So the dashboard task has a fan-in dependency on all 5 branches. It sits there and waits until branch 1 is done, and branch 2 is done, and branch 3, 4, and 5 are all done. Only then does it start. Now here's the gotcha that catches a lot of people. Your fan-in task is only as fast as your slowest upstream branch. Think about it. If 4 branches finish in 10 minutes, but the fifth one takes 45 minutes because it's processing a massive table. Your dashboard task waits 45 minutes. All those fast branches finished ages ago, but they're just sitting there, their results getting stale while everyone waits for that one slow branch. This is why understanding your critical path matters. The critical path is the longest chain of sequential dependencies through your entire DAG. It determines the absolute minimum time your pipeline can take. You can optimize the fast branches all you want, make them run in 2 minutes instead of 10. But if that slow branch still takes 45 minutes, your total pipeline time hasn't changed at all. The bottleneck is the bottleneck. And in a fan-in scenario, bottlenecks become very visible. Okay, so we've got fan out for parallelism and fan in for synchronization. But what about the outside world? What happens when your pipeline depends on something external? That's where sensors come in. Sensors are a special kind of task. They don't transform data, they don't write tables, they don't compute anything, they just wait. They wait for some external condition to become true, and then they signal to the rest of the DAG that it's okay to proceed. Think of a sensor as a lookout. It's standing at the gate, watching, checking, waiting. Has the file landed in S3? Is the upstream table partition from today available? Has the partner API returned a 200 status code? Is it past 6 a.m. UTC? Has the upstream DAG in another team's Airflow instance finished running? These are all real sensor use cases. File sensors that watch for a specific path to appear. Database sensors that check if a partition exists. Time sensors that wait until a certain hour. External task sensors that poll whether another DAG has completed. API sensors that ping an endpoint. Now here's where sensors get tricky, the poke versus reschedule dilemma. When a sensor is waiting, what should it actually be doing? In poke mode, the sensor occupies a worker slot and checks the condition every few seconds. Is the file there yet? No. Wait 30 seconds. Is it there yet? No. Wait 30 seconds. Over and over. The problem? That worker slot is occupied the entire time. If you have 16 worker slots and 5 sensors are all poking, you've only got 11 slots left for actual work. If the file doesn't show up for 2 hours, that sensor has been hogging a worker slot for 2 hours doing nothing. In reschedule mode, the sensor checks the condition, and if it's not met, it releases the worker slot and reschedules itself for later. This frees up the slot for real work, but it adds latency because the sensor might not check again for 5 or 10 minutes. So there's a gap between when the file actually arrives and when the sensor notices. But here's the really scary one, sensor deadlocks. Imagine you have 16 worker slots and you've got 20 sensors all in poke mode, all waiting for files that haven't arrived yet. 20 sensors, 16 slots. The sensors fill up every available worker slot. And now your actual tasks, the ones that extract, transform, and load data, they can't run. They're queued up, waiting for a free worker slot. But no slot will free up because the sensors are all sitting there, poking, occupying slots, waiting for files, and some of those files might be produced by the very tasks that are stuck in the queue. Complete deadlock. Nothing moves. Your pipeline is frozen and it's not even throwing an error. It's just sitting there, perfectly stuck. This is one of those failure modes that's almost invisible until it hits you. And when it does, it takes the whole pipeline down. Now let's put all of this together, because in the real world, you don't use fan out or fan in or sensors in isolation, you combine them. Let me walk you through what a realistic production pipeline actually looks like. It starts with a sensor, a file sensor sitting at the front of the DAG, watching an S3 bucket for today's data drop from the source system. The partner says they upload the file by 4 a.m. Sometimes it's early, sometimes it's late. The sensor handles this gracefully. Once it detects the file, it triggers the extract task. The extract task pulls the raw data from S3, validates the schema, and loads it into your staging area. Now we fan out. From that single extract, 5 parallel branches kick off: user metrics, revenue aggregation, fraud scoring, feature store update, and campaign segmentation. They all run independently in parallel. Fan out gives you the speed. Then fan in. A merge and validate task sits downstream of all five branches. It waits for all of them to complete. Once they do, it runs a set of data quality checks. Are the row counts reasonable? Do the checksums match? Are there any null values in required columns? If all checks pass, the final load task writes the results to the production warehouse. Dashboard refreshes. The CEO sees fresh numbers at 9 a.m. The total runtime, the sensor might wait 30 minutes for the file. The extract takes 5 minutes. The 5 branches run in parallel in about 15 minutes, limited by the slowest branch. The merge and validate takes 3 minutes. The load takes 2 minutes. Total wall clock time about 55 minutes. But if you ran all those tasks sequentially, no fan out, each branch back to back, you'd be looking at over 80 minutes. And if you didn't have a sensor and just scheduled the pipeline at 4 a.m., you might run before the file even arrives and get an empty dataset. The combination of sensors, fan out, and fan in is what makes this pipeline both reliable and fast. And the critical path, the longest sequential chain through the DAG, is what determines your minimum runtime. In this case, it's sensor plus extract plus the slowest branch plus merge plus load. Now here's where people get tripped up. The anti-patterns, the mistakes that look harmless but cause real damage. Let me walk you through the big ones. First, over-fanning out. Yes, parallelism is great, but if you fan out to 200 parallel tasks, you're going to overwhelm your cluster. 200 concurrent Spark jobs, all fighting for the same resources. Memory pressure, network saturation, scheduler overhead. There's a sweet spot. Maybe it's 10 parallel branches, maybe it's 30. It depends on your infrastructure. But more is not always better. Second, missing dependencies. This is the one from our earlier scenario. A task that should depend on another task but doesn't. The aggregation that runs before the currency conversion. This is the silent killer. No error, no failure, just wrong data. Always triple check your dependency graph. Draw it out. Walk through it mentally. Ask yourself, for every task, what must be true about the data before this task runs? Third, circular dependencies. This one is usually caught by the orchestrator. Airflow will reject a DAG with cycles, but sometimes you get subtle near cycles. Task A writes to a table that task B reads, and task B writes to a different table that a later version of task A reads. Not a direct cycle, but a logical one that causes confusion about which version of the data is correct. Keep your data flow strictly one directional. Fourth, sensor timeouts. What happens when the file just never arrives? If your sensor doesn't have a timeout, it waits forever. Your pipeline hangs, your SLAs breach. Always set sensor timeouts. And when a timeout fires, have a clear alerting and fallback strategy. Maybe you skip today's run and alert the team. Maybe you use yesterday's data as a fallback. But don't just let it hang. Fifth, dynamic DAGs. Modern orchestrators let you generate fan-out branches dynamically at runtime. Instead of hard coding 5 branches, you query a table and create one branch per row, maybe one branch per customer segment or one per data partner. This is powerful but dangerous. If that table suddenly has 10,000 rows, you've just created 10,000 parallel tasks. Set guardrails. And circling back to our first video, every single task in your DAG should be idempotent. If a task fails and gets retried, it should produce the exact same result as if it succeeded the first time. That's what makes automatic retries safe. That's what makes backfilling possible. Idempotency and clean DAG dependencies go hand in hand. Alright, let's bring it all together. We covered a lot today. Fan out gives you parallelism, one task spawning many. It's how you make your pipeline fast by running independent work at the same time. Fan in gives you synchronization, many tasks converging to one. It's how you ensure downstream tasks only run when all their dependencies are satisfied. And remember, you're only as fast as your slowest upstream branch. Sensors give you external coordination. They bridge the gap between your pipeline and the outside world. But watch out for the poke versus reschedule trade off. And for the love of all things data, set your sensor timeouts and watch your worker pool. And the DAG itself, the directed acyclic graph, is the blueprint that ties it all together. It's the map that tells your orchestrator what to run, in what order, and what to wait for. Here's the one question I want you to take away. For every single task in your pipeline, can you point to its upstream dependencies and explain exactly why it needs to wait? If you can't, you've got a bug waiting to happen. If you found this helpful, check out the rest of the Essentials of Data Engineering series. We've covered idempotency, atomic rights, late arriving data, schema evolution, dead letter queues, slowly changing dimensions, partitioning, exactly once processing, and backfilling. And this episode on DAG dependencies ties a lot of those concepts together. And don't worry, the subscribe button has zero upstream dependencies. You can click it right now. No sensor required.